Suppose we have a region in the plane, call it D. Here I mean the xy plane, so I'm drawing this as though it's embedded in three-dimensional space, but here's our xy plane, this region D. And suppose that this region D represents a thin metal sheet or a thin sheet made out of some material whose density is given by a function rho equals rho of xy. So the idea here is that for any point in D, any xy point in D, the density at that point of the material is given by this function rho. Our question here for this example is we want to, if we were to take a fulcrum, which is just something with a point, and we were going to try to balance this sheet, this thin metal sheet on the fulcrum, where would we place the fulcrum? So at what point would we place the fulcrum so that this sheet is perfectly balanced? So maybe the sheet is very heavy over here, and so for the sake of this example, maybe we want to place the fulcrum right here. So there's much more mass on this side that levels things out. And this point here that we're trying to find, x bar comma y bar, this is the center of mass of the lamina. This sheet, this thin sheet, by the way, this is called a lamina. So a thin sheet with some density. So the center of mass is what we want to try to find, x bar comma y bar, the coordinates of this point. And obviously the first thing we should then do is try to compute the mass itself of this thin sheet. To do that, let me just pull this lamina out and so we can take a better look at it. It might be a different shape here, but the idea is that this is the same sheet. And remember, we have this density function at each point on the lamina. And so what we want to do is we want to partition this sheet. So we want to partition the y-interval. So we'll take slices parallel to the x-axis. This represents a partition in the y direction of our sheet. And then now you can probably guess we're going to also partition in the x direction, which is going to be, we're going to slice up our region with slices that are parallel to the y-axis. And so the idea here is that we've sliced up our region into many small rectangular regions. Some of these rectangular regions have portions that are not inside the lamina at all. So we will just say that the lamina, the density at those points is 0. And then what we want to do is look at, say, a representative rectangle here. Let's call this rectangle Rij. And we want to try to find out what is the density of that, just that portion right there. And so to do this, I'm going to go quickly through this because I think we can probably see what's going to happen here. But to do this, we need one fact from physics, which is that the mass of a region is equal to the density. So the mass of a two-dimensional region is equal to the density of that region times the area. Okay, and so that's what we're going to do here. But to do that, we need to pick a test point inside this region. So this point right here we'll call xij star, yij star. This could be any point in the region. Again, you can probably see where this is going. We're going to eventually take a limit, and it's not going to matter which point we choose. But if we choose this point, then we can compute the density at this point. So rho of xij star, yij star. We're going to use this as a constant density on the entire rectangle. We just pick one test point. And then the mass of this small rectangle, so we'll call this like delta mass ij. This is going to be then our density of this small rectangle times the area of this small rectangle, and I'll call that delta aij. And of course delta aij, since these are rectangles, can probably be broken up into delta xij, delta yij. We're not too concerned about that right now because what we're going to do next is just write down, okay, if this is our mass element, delta m, delta mass, then our mass itself is approximately equal to the sum over all these rectangles. So the sum as I goes from 1 to, let's say, n, and sum j goes from 1 to m of delta mij, which is of course just this formula right here. So the mass is approximately equal to this double sum over all the rectangles that we've used to chop up this region. And again, it's rho xij star, yij star. This is just a test point times delta aij. And right now you're probably saying, Justin, why are you wasting our time? We know exactly what's going to happen, right? And so now the next thing that you do is to get the exact mass, you just take a limit. So take the limit as m and n approach infinity. So we take infinitely many boxes, that makes them very, very small, and as we take the limit, as long as this limit exists, then we'll get the mass. So the mass of the laminar region is going to be equal to the limit as both n and m approach infinity of sum I goes from 1 to n, j goes from 1 to m, rho at these test points, xij star, yij star, delta aij. And of course, this is just, we've seen this now before, this is just the definition. This is going to be a double integral. So this becomes a double integral over the entire region D of rho of xy dA. And so the mass of our region is the double integral of the density function. Okay, so that's the mass of the entire region. What we want to do now is find the center of mass. And to do that, we need to find the moments of mass. So the moments, you might remember from Calc 2, the moments are proportional to, so if this is a rectangle with constant density, then mx is proportional to, so I'll just write this, it's proportional to the distance from the y-axis times rho of xy. And so if we go back to our picture here, where we have everything partitioned, the only difference is if we want to find the moment in the x direction, so this is the tendency of this region to want to tilt one way or the other, be pulled one way or the other in the x direction, we need to multiply by the density times the y value. Okay, and so this ends up being, I'm not going to work out the Riemann sum, but there's a Riemann sum argument here. So there's a Riemann sum argument, I will say that. Feel free to look this up yourself. And after this argument, we end up with this formula for the moment with respect to x being the double integral over the region D of y times rho of xy dA. And similarly, the moment with respect to y is this pretty much the same, except we swap out y for x. And so this is x times the density function integrated with respect to area over D, over the region D. So these two formulas right here, these are the moments in the x and y direction. And so now we want to use these to write down the center of mass. So once we know this, then the center of mass, remember we called this point x bar comma y bar, this is given by the following formula, that x bar is equal to the moment with respect to y divided by m, and y bar is given by the moment with respect to x divided by m. Okay, and all three of these things, mx, my, and little m, those are all given by integrals. And so we can write down one final integral formula here. The moment with respect to, the center of mass with respect to x is given by the integral over d of x rho of xy dA divided by double integral over d rho of xy dA. This is the mass, this is the moment. Same thing, y bar is given by double integral over d, y times rho of xy dA, divided by the mass, double integral of rho dA. Okay, so we're going to use these formulas moving forward.